Theoretical physics is a branch of physics that deals with the development of mathematical models and frameworks to explain and predict the behavior of the physical universe. Theoretical physicists use a variety of mathematical and conceptual tools to construct models and hypotheses that describe the fundamental laws of nature and the behavior of matter and energy at a wide range of scales, from the subatomic to the cosmological. Theoretical physicists often work in collaboration with experimental physicists, who perform experiments to test and validate their theories. Together, theoretical and experimental physicists work to advance our understanding of the fundamental laws of nature and to explore the mysteries of the universe. Without our understanding of the underlying mechanism of the nature, all kinds of today technology would be impossible. For examples, communication networking, global positioning system, GPS, high-performance computer and magnetic resonance imaging. The Institute for Fundamental Study, or IF in short, was officially inaugurated on March 14, 2011 by Naresuan University Council as a research center unit. From the first day to the present, IF members are working on the cutting-edge areas of research in theoretical physics to expand the boundaries of our understanding of the fundamental laws of nature, including cosmology, gravity, string theory, quantum information science and mathematical physics. We would like to emphasize that frontier research in theoretical physics is essential for advancing our understanding of the universe and developing new technologies that would benefit not only Thailand but the world society.
Good afternoon, everyone. Welcome to Tah Poe Seminar Series 56 of Group 5. We have our speaker, Dr.Suppanat Supanyo. He is going to talk about the neutrino mass scale from nonstandard Lagrangian. Welcome.
Swadikap everyone. Afternoon everyone. Today I will talk in the topic the neutrino mass scale from the non-standard Lagrangian approach. Actually, this topic I have taught in the winter school, in the previous winter school at the IF, but after the talk in the winter school, I get rejected from the EPJC journal. Today I will show you why I get rejected, and I show you the comment from the referee and how can I fix it, try to fix it. Okay, let's start with the introduction part. I will introduce you the origin of the mass of the fermion in the standard model first, and I will show you why the neutrino mass is a problem in the standard model. In the standard model, we have 12 fermion in the standard model. Every particle have a mass shown in this figure. Traditionally, a mass of the particle in the standard model can be explained by the term, a mass term in the Lagrangian like this. But when you consider the symmetry in the standard model, a mass term is a forbidden term in the standard model. It is violate the electroweak symmetry. Mass term is not allowed if a fermion is a Dirac particle. The question is, how do this particle acquire a mass? The answer is the Higgs mechanism. in the Higgs mechanism, in the standard model, we can write the term that we can write the Yukawa interaction between the fermion and the Higgs like this. The phi field is a Higgs field, and L and the Q is the lepton and the quark, left-hand lepton and left-hand quark doublet field. Here, Y is so-called Yukawa coupling. It shows the strength of the Higgs and the fermion interaction. This term is invariant under the electroweak symmetry SU2 L cross U1. Here, look at the Higgs Lagrangian. Here, this equation is the Higgs Lagrangian, and the V term is the Higgs potential. The shape of this potential is a Mexican hat shape, like this. You can see that at phi around the 0 point, the energy of the theory is not the lowest energy state. So it means that the SU2 cos U1 symmetry is not stable. It's not a real stable point. And with the quantum fluctuation of the Higgs field, the Higgs must be spontaneously low down to the local minimum at the V, that is the lowest energy state of the theory. Then we expand the Higgs field around the vacuum expectation value of the Higgs of itself. You can see that from the Yukawa interaction term, you can split the Higgs field in terms of the wave with a small fluctuation field H. Here, you will get the first term is just a constant. It's a mass term. And the second term is the interaction. So, a mass of the particle in the standard model depends on two values. The first one is the Yukawa coupling, the size of the Yukawa coupling, and the second one is the Higgs wave that is around 246 GeV. It means that if a particle is heavy, the Yukawa coupling is also heavy. You can see the problem in the standard model. This parameter is spanned in the widely separated scale without any explanation. You can see we have the top quark mass around the 173, and when you can calculate the Yukawa coupling of the top quark, the size is around 1. But if you see the electron, mass is of just around 1 MeV, and the Yukawa coupling is around 10 to the minus 6. It spans out in a very widely separated scale without any explanation, unlike the gate field. You can, in the gate field, we have a symmetry that's constrained aside of the gate coupling. But in the standard model, we have no any symmetry to explain why this exists in this scale. If you think that this situation is the worst case, you have to see in the neutrino. Originally, the neutrino is, in the standard model, is a massless particle, because we have no right-hand neutrino field. And if you have no right-hand component, It means that the mass term of the neutrino is not exist in the standard model. But with the current observation on the neutrino oscillation, we find that neutrino has a mass in a very small scale. In the below the electron volt scale, maybe around the milli-electron volt scale to the centi-electron volt scale. Okay, with the observation, we have to add a mass term of the neutrino into the standard model with the Yukawa interaction. If we assume that the neutrino is a Dirac particle, right? The other particle, like the other fermion in the standard model, the neutrino should acquire a mass from the same mechanism, the Higgs mechanism. After the Higgs symmetry breaking, the neutrino should have a mass formula in the same form with the other particle. But when you substitute a mass of the neutrino into this formula and calculate the Yukawa coupling, you can see the size of the Yukawa coupling is around 10 to the minus 15. And what happened? Compare the size of the neutrino Yukawa coupling to the length of the standard model particle. It's so much, it is really different scale. Traditionally, if we have two objects that appear with the widely separated scale like this, one can assume that the neutrino may acquire a mass from the different mechanism. Its mass itself may be the different mechanism from with the Higgs mechanism. The famous scenario is the seesaw mechanism, the type 1 seesaw mechanism. In this presentation, when I talk about the seesaw mechanism, it means the seesaw type 1 mechanism, type 1 seesaw mechanism. คุณพระ Okay, because of the neutrino is only a single neutral particle, single neutral particle of neutral particle in the standard model. We can assume that it might not be the Dirac particle, but it may be the Majorana particle instead. If the neutrino is a Majorana particle, it means that it's allowed to add the Majorana term, Majorana mass term into the Lagrangian, like this. Here we have the mix between two mass terms. The first one is the Dirac mass. This term coming from the Higgs mechanism. And the second term is around by gauge symmetry. The parameter MR is a dimension-full parameter, a new dimension-full parameter added into the standard model. Here, with the mixing between two types of a mass term like this, a mass matrix of the neutrino is not in the diagonal. It means that the neutrino can propagate with the oscillate between types of particle. This is the unphysical state of the particle. So to specify the physical state of the neutrino, mass eigenstate neutrino, we have to diagonalize the mass matrix of the neutrino with this transformation. And when the theta is the mixing between the left hand and the right hand component defined by the Dirac, the size of the Dirac mass term suppressed with the right hand mass term. The interesting for this mechanism is when you consider in the limit that MR is very larger than the MD, the left hand and the right hand is decoupled, can be decoupled, and we can, in the mass eigenstate, the left and the right is separated together. Here, look at the mass for the left hand component of the neutrino. Okay. I forgot. Okay, look at this, the M1 parameter. The M1 parameter is the MD subplaced by the MR. It means that if the MR parameter is large enough, we can obtain a naturally light particle state M1. If the MR is large enough, here so now if the MD coming from the Higgs mechanism, and we assume that the lambda D is around the standard model particle. If the Yukawa of the neutrino is around the standard model particle, we require the parameter MR is around, can be between the TeV scale to the grand unification scale to provide the neutrino mass scale. And this is a very clean solution. I think it must be one of the most beautiful solutions. It looks so clear. But there are a problem in this framework. I don't sure it can call it a problem, because nowadays we have many problems that we can apply the Majorana mass to explain the problem. For example, if the LSND oscillation anomaly, I forgot the full name, sorry, but you can use these two search no. Okay, in this oscillation we can be solved mathematically solved by, if we have the MR around the EV scale, we can use the MR around EV scale to solve this problem. And the other problem is the dark matter problem. We can apply the concept of the Majorana mass to contribute to this problem. In the warm dark matter problem, we require, if the dark matter is a Majorana particle, Majorana neutrino, it requires a mass in the regime around a KeV. But this very low scale compared to the previous section, right? If the right hand of Majorana neutrino is exit in this scale, we find that we require the Yukawa coupling is around 10 to the minus 10 approximately. It means that the type 1 seesaw is not an appropriate solution to explain the neutrino mass anymore. What next? To explain this situation, you can apply many various types of the seesaw. There are many various types of the seesaw mechanism. And moreover, with the current observation, the type of the neutrino is still unknown. It have never confirmed by any experiment. The type of the neutrino can be specified by the process, so-called the neutrino-less double beta decay experiment, shown in the right-hand figure. If the neutrino is the Majorana type, this process should realize in the nature and see observed in the experimental observation. But if the neutrino is the Dirac particle, this process should not exist. The problem is if the neutrinos are confirmed as the Dirac particle, so all of the seesaw mechanism that we have in the current theory today may be broken. And what next to solve this situation? And I just prepare. In this presentation, I will apply the non-standard Lagrangian approach in two different schemes, two different problems. The first one, if the Dirac, I will explain the Dirac neutrino, the origin of the Dirac neutrino mass from the non-standard Lagrangian approach. And the second one, I apply the non-standard Lagrangian approach to extend the length of the right-hand Majorana neutrino in the type 1 seesaw mechanism down to below TeV scale without the problem of the too small Yukawa coupling. Okay, I try to solve this problem in the minimalistic way. What is the minimalistic way is, I think it's pioneered by the new Torok. No extending of the standard model symmetry, no adding of the new scalar boson. Here, only one dimension full parameter is added to the standard model. In fact, I add right-hand neutrino into the standard model as well. Not only dimension full parameter, but you can question that why we have to extend the model like this, because the lesson is because in the past decades, we have no new particle. It is what observed in the collider, no new any particle. So I just prepare the mechanism to explain these problems without adding the new particle. The non-standard Lagrangian approach in my work is motivated from the non-uniqueness of the Lagrangian, from Ajahn Sikhalin Yu Kong work, and they will show the Lagrangian can be written in many forms, and the equation of motion is still the same. For example, you can, instead the t minus v, you can rewrite the Lagrangian in form of the multiplicative function between the kinetics and the potential function. And the equation of motion is still the same form. So with the lesson, I extend that concept to the field theory. I assume that the Lagrangian of the complex scalar field is written in the form of the multiplicative form, and this Lagrangian provide the equation of the motion approximate into the Craig-Gordon equation, like the Higgs field, like the normal complex scalar field. Here, the capital F function and the F function is the unknown function. So I solve these two functions by the inverse problem of the calculus variation. By substitute this Lagrangian into the Euler and then apply the constant of the equation of motion into the Euler-Lagrange equation and solve the explicit form of the Lagrangian. We get the form of these two functions like this. Here, so we obtain the solution of the multiplicative form of the complex scalar field. Originally, the goal of we apply this Lagrangian to explain the hierarchy problem in the standard model. In the standard model is the linearizable model and the UV cutoff. The value of the UV cutoff in the standard model is unknown. You can take the cutoff of the theory into the Planck scale, but if the UV cutoff of the standard model is too large, it leads the size of the quantum correction contribute to the Higgs mass is very large. It leads to the fine-tuning problem. To avoid the fine-tuning problem, the standard model cutoff should artificially low down to the TeV scale without no physical explanation. I solved this problem by set the parameter is around value and the detail. And then after I sent to publish, and in this paper I get some hint to explain the neutrino mass scale, and then I create the new paper about neutrino and got rejected. Here, the referee comment me that by this parameter that I solve the hierarchy problem, it did not make sense to explain the neutrino mass, because when you explain the neutrino mass, you require to explain why the neutrino, you have to explain why neutrino Yukawa coupling is small. I just reduce the Yukawa coupling of the neutrino into the same scale of the fermion. But the original parameter in our model, the dimension full parameter, is in the widely separated scale. It means I use the unnatural model to explain the naturalness of the neutrino mass. So that's the first comment, and I think we agree with the referee. The second comment is they told me that there are many ad hoc parameters in the model. For example, to explain the hierarchy problem that we proposed in the first paper, I go to a fantasy way. Okay, by the concept of the non-uniqueness of the Lagrangian, it allows us to write the Lagrangian of the Higgs in form of the linear combination form between standard form and the non-standard form like this. But and the UV cutoff around TeV exists naturally under the autonomy of the physical scale of the naturalness. But this Lagrangian leads to the stability problem in the Higgs potential. The electroweak vacuum expectation value is not the lowest energy state. This form of Lagrangian can provide the other ground state, the other lowest energy state. And I artificial adding the new term into the Lagrangian, but they add under the gate invariant principle. That's why the referee told me to apply the ad hoc model, and they do not allow us to publish in that journal. So in the revised version, I will show you how can I try to fix those problems. So I do not use this form of Lagrangian anymore, and I just replace the standard form of the Lagrangian into the multiplicative form that I have solved from the inverse calculus variation. And I will show you that with just this form, I can explain the hierarchy between the neutrino Yukawa coupling and the fermion into just a compact scale, 1 to 100 scale, and all the parameters in the theory, the dimensionless parameter constructed by the parameter in theory lie on the same scale. I hope I do not miss anything. Okay. Let's analyze a bit about the standard model that replaces the Higgs Lagrangian with the multiplicative form. Here we replace the Higgs Lagrangian with this form. I add some constant term to remove a large contribution to the cosmological constant. Here, V term is a Gisberg-Landau type. It's a Mexican hat-shaped potential like the standard model. When V is the Gisberg-Landau type, we find that when you multiply exponential term to the first and the kinetics term, we can define the new potential of the Higgs term that modified by the exponential function like this. The epsilon is a parameter that exists when I solve the multiplicative Lagrangian function. Here, the potential of the Higgs is modified in the UV regime in the large field limit. When the Higgs field is very larger than the parameter lambda, we have two distinct shapes of the Higgs potential. But when you consider the low energy, the small field regime is still the same form with the Gisberg-Landau potential. No deviation exists. And the lowest energy state in the figure A can be evaluated by the vacuum solution from the equation of the motion of the Higgs Lagrangian. And we find that the exponential is not zero, cannot be zero. So you can get the Higgs wave is in the same form with the standard model prediction. It does not depend with the new parameter lambda. Then I perform the standard scheme in the Higgs mechanism. I just expand the Higgs field around the Higgs wave, and I skip the detail of the Fourier definition and fitting parameter to the Fermi coupling constant. You can follow in the archived version if you need to see the detail. After this fitting of the parameter, we find that our model predict the cubic coupling constant, all of the cubic coupling constant is in the same form with the standard model prediction. So we have no deviation in this process, but the deviations start at the vortex cupping. The lambda 4 is the cupping constant of the Higgs with 4 external legs into the vertex. And the second one, GHHVB, maybe so-called the quartic gate Higgs interaction. We have the two Higgs field cupping with the massive gate field cupping together in the vertex. So these two cupping is modified by the parameter lambda. The right-hand side is the standard model prediction. Nowadays, we have the constant for the GHHVB. We find it from the experimental observation. This parameter should, by comparing this parameter in the observation, the size of modification should be in this range. So from our model, we find that this parameter depends on the parameter lambda. We can plot the deviation from the standard model and show in this figure. We find that if the lambda is lower than the 170 GeV, we find the GHHVB of our model is out of the experimental, the bound from the experimental observation. So with this lesson, we can set the lower limit of the parameter lambda to compatible with the experimental observation. Here, the upper limit of the lambda is still unconstrained from any observation. So I apply the concept of the naturalness. The dimensionless ratio of the parameter in the theory should be the same, around the same order of the magnitude. It's just a beauty concept in mathematics. So in this paper, I use allow us to, in the scale 1 to 1,000 scale, but someone is not agree with this value. Someone needs the naturalness should be in the scale 1 to 10, but it depends on the work. So we have the upper limit. So it means that the lambda parameter should not greater than 1,000 scale of the Higgs mass. Just with, okay. Then we apply those limits to analyze the mechanism to produce the small of the neutrino mass. Here, what happens if the Higgs is in the multiplicative form? Traditionally, in the standard model, you can write the gauge invariant operator, just the linear combination form. But when the Higgs Lagrangian is modified, I forgot to refer the A is the gauge invariant operator. It allows us, if the Higgs is in the multiplicative form, it allows us to write the gauge invariant operator not only in the linear combination, but this operator can incorporate both outside and the inside of the Lagrangian without any the symmetry violation. Let's see the effect if we add the operator like this into the Lagrangian. Here, after the symmetry breaking, the operator A get a coefficient like this. It looks ugly, right? Here, when you consider the parameter lambda is very larger than the electroweak scale, we find that this coefficient can be approximated into the simple form. It is the electroweak scale subplaced by the new scale parameter lambda. By applying this limit, we find that the operator A, the coefficient of the operator A can be between 10 to the minus 1 to 10 to the minus 12. It means that if you add the operator inside and outside of the Lagrangian, of the Higgs Lagrangian, you can obtain a natural small coefficient exists from this mechanism. We find that the ratio between the neutrino mass and the fermion is similar to can be fit into this length as well. So if we think that the neutrino is the Dirac particle, the gauge invariant operator, if the neutrino mass is the Dirac particle, firstly, the Yukawa coupling can be right outside of the Lagrangian, and to get a natural small coefficient, you should write both outside and the inside together like this. After the symmetry breaking, we find that the neutrino mass get a small coefficient subplaced by the lambda. By compare with the standard model particle, this is naturally small without fine-tuning of the Yukawa coupling of the neutrino. By put the constant of the neutrino mass in the EV scale and analyze the mass of the neutrino mass against it, and so plot the parameter lambda. Okay. The blue band is the size of the Yukawa coupling of the neutrino. Depend on the value lambda, and the purple band, and the blue band is the first generation, the Yukawa coupling of the first generation particle. The green band is the second generation particle, contain new Sten quark and sham quark. And the red band is a third generation particle. You can see that if the lambda is large enough, around 5 TeV, the size of the neutrino Yukawa coupling can lie on the first generation particle. It has the same scale. Under this regime, we find that we have no difference between the size of the neutrino Yukawa coupling and the size of the sharp fermion in the standard model. The neutrino can have the size of the Yukawa coupling around the electron to the bottom quark. So the neutrino can acquire a natural small mass by this mechanism if the neutrino is Dirac. We do not need the seesaw mechanism in this way. Then, if the neutrino is a Majorana type, I will show you this approach is also useful to extend the type 1 seesaw mechanism. So here, the operator A is not the Dirac Yukawa interaction, the Yukawa interaction and also the right-hand Majorana mass. In the traditional seesaw mechanism, we have only the first line, but here we write this term both outside and inside of the Lagrangian like this. Let's see what's happened. After the symmetry breaking, we can see that both mass terms get suppressed by the small coefficient. Then when you perform the seesaw mechanism, the mostly left-hand state of the neutrino is naturally small as the seesaw mechanism, but the M2 can be small as well. Even the MR is in the electroweak scale or a large parameter. For example, if the lambda is allowed 6 TeV and the MR parameter is allowed the electroweak scale, like around the Higgs mass, so there is no naturalness problem between the MR and the Higgs mass anymore because we can set in the same scale. The lambda is in the standard model particle like the muon, just for example. With this set of the parameter, we can obtain the M1 can lie on the neutrino mass scale, and the M2 is the mostly right-hand neutrino can naturally exit in the KeV scale by the input parameter in around the electroweak theory. So the naturalness can be restored with this modification. The M2 is naturally small. And this will show another way to modify the seesaw mechanism to avoid a large value of the MR parameter in the seesaw mechanism. From the gauge invariant, not only the mass term that you can put inside and outside of the Lagrangian, you can add the kinetics term of the right-hand Majorana neutrino in both sides. The effect of this adding term like this, after the symmetry breaking, we find that the kinetic term of the right hand get a small coefficient. So you have to reorganize the kinetics term by the Fourier definition. After the Fourier definition, to reorganize this into the canonical form, we find that a mass of the right hand is shift up, is scale up, is scaled by the factor lambda to the fourth. So it means that we can effectively mass of MR is naturally large. We find that if we can, in this approach, if we set a mass of the MR around a Higgs mass, around the electroweak scale, the seesaw mechanism is still work. So no widely separated scale between the right-hand neutrino mass and the Higgs mass in this model. In this scheme, so the naturalness is also restored, and the difference with the previous section is the M2 is naturally large, and in the previous modification we have the M2 is naturally small by so this is finished for the seesaw, the neutrino part, but I have to tell that I have to discuss a little bit about the problem in the third generation and the first generation particle. So from this studying of the Lagrangian, not only we can provide a small scale of the neutrino, and we also provide a large scale of the fermion mass as well. If you add the Yukawa coupling both inside and outside, we get a small mass. If you add the kinetics term into the Lagrangian both inside and the outside, we obtain a large mass of the fermion. Here, let's see the Yukawa coupling of the standard model particle. The blue shading is the first generation, and the red shading here is bound shading. Is you can see that there is a huge hierarchy appear, allow 1,000 scale to 10,000 scale without any explanation. So we hypothesize that the third generation, the Lagrangian of the third generation may be written in a different way with the first generation particle under our model perspective. In this part of my work, I studied just a toy model. We add the right hand, but not the Majorana kinetics, but it is the Dirac right hand kinetics term, both inside and outside of the multiplicative Lagrangian. We find that after the symmetry breaking, the right hand, already the right hand get the non-canonical form. So we have to perform the Fourier definition like this to reorganize this part. Then after the Fourier definition, we find that a mass of the Dirac particle that Lagrangian is written like this is scaled up by the square lambda. It is different from the Majorana type. The Majorana type is a quartic lambda. Here, a mass term of this particle can be written like this. It just looks like a magic number, a 6 TeV. I don't know why, but I think a 6 TeV of the parameter lambda is an interesting scale, because of if the lambda is allowed a 6 TeV, we find that the scale factor is around 10,000, around 1,000 scale. It means that by comparing, this particle should naturally heavier than the normal particle is coming from the Higgs mechanism around 1,000 times. That is corresponding to the third generation particle, coincidentally. So in this work, we can categorize particle in T group. We can assume that the neutrino is in this scale, and the first and the second generation is just a normal acquired mass from the normal Higgs mechanism, and the third generation is different way. The kinetic is both inside and the outside. And then evaluate the Yukawa coupling of this 12 particle. We find that this is the Yukawa coupling varying on the scale lambda of those particles. It seems like all of the particles in the standard model, the size of the Yukawa is compact in a narrow scale around lambda around 6 TeV. Here, we find with the multiplicative Lagrangian approach, the size of the Yukawa coupling that span around 1 to 10 to the minus 15 can be reduced into just 100 scale. By this, a huge hierarchy is reduced around 10 order of the magnitude. Finally, we hint some open problem from this work. As you can see that around 6 TeV, the size of the Yukawa carbon is compact is the most compact scale. But if you can see this contribution is the red line is the top quark, and the other two second green dashing line is a mu and stent. If we ignore this T particle, we find that the other particle, the size of the Yukawa seems to be compact in a natural length 0.1 to 1 scale, like the scale of the gauge, the ratio of the gauge coupling. So I think that this I can hypothesize that there might be at least 2 mass generation that is not found in this paper, hidden in the multiplicative Lagrangian to generate this T particle. A mass scale that we miss, and I hope to find it, is depend on the lambda and the lambda to the third to explain the top quark mass. But now I still not found this pattern and hope to find. In conclusion, so from the multiplicative Lagrangian approach, in the revised version, we have T generation of particle mass, fermion mass, categorized by the scale factor. We can reduce the size of the Yukawa coupling in the standard model that have span in the widely separated scale into just 100 scale. And the other parameter, other dimensionless parameter that construct from the dimension full is also in the same scale with the size of the Yukawa coupling. All of the parameters is in the same scale. Thank you for your attention.
Then questions from the audience? Especially from okay. I have got some questions. So, can you go to your slide 11? Okay. So from my understanding, correct. I mean, in order to determine whether the particle is Dirac or Majorana, you look at whether they are charged. So I mean, if you want to see whether your neutrino is Dirac or Majorana, you just determine whether your neutrino has charge.
Oh, no. The neutrino can be a neutral, although it's a Dirac particle. For example, in the originally the standard model, originally is a Dirac particle, and it may be the Dirac.
I have to ask you to go to slide 25.
Yes. Wait a minute.
Okay, so maybe. On the top right, it looks like I mean, in your work you only consider the expansion in like in the first term of the exponential, right?
Yes.
Yeah. And it's like your first term is something that is originally in the Lagrangian. Is that right?
Oh, there are many terms, but
Yeah,
I just consider.
I mean the first term on the top, right? So one of the terms or maybe some terms from the standard model Lagrangian, is that right? Minus epsilon a hat. For example, your like
The first term is
yeah
this
like
term.
that thing.
Okay.
And then you kind of put it in like outside and inside. Is that right? So it's kind of like you say, oh, since you expand up to the solid first order, it looks like you say, oh, I don't like the term from the standard model, so I delete it, and then I introduce it by the term that I want.
I do not delete anything in the standard model.
So if you expand the exponential, you will get something like 1 minus b. So it means that you have epsilon a hat minus epsilon a hat. So it seems you kind of delete
The other term is the interaction term between Higgs and the neutrino. And there are many terms when you expand the exponential term in the limit that the Higgs field fluctuation in the small regime. But that term is not a mass term. It's an interaction that we hope to observe. But to specify a mass term, you just need only lowest order approximation.
Yeah. But my question is essentially that you have minus epsilon a hat plus epsilon a hat, right? At the lowest order, which means that you at the lowest order you remove the term that is originally in the standard model, and in the next order you introduce the potential multiplied by the term from the standard model. Is this essentially what you are doing?
Sorry.
I mean, if you expand your exponential,
Yes.
Yeah. So at the lowest order, you kind of have minus epsilon a hat plus epsilon a hat, right? So they cancel out. And this, but if you go to the next order, then you will have something like v multiplied by a. So it's kind of like you essentially say, oh, you don't like the term from the standard model, but you prefer it to be multiplied by v.
The term multiplied by v.
Is that right? I mean the term at the first order in v, if you expand your exponential, the term at the first order in v will look like v times a.
Yes.
Yeah. Okay. And in that case, do you need to worry? For example, do you need to worry about? I mean, when you want to find the vacuum, do you need to worry about that your potential also appears by multiplying with other terms?
In this case, I still never calculated the potential that shift by the A, but I think I don't sure that it should be the multiply the term that the operator A and the V exponential we should consider to find the vacuum expectation value, because this term is an interaction term. But when I calculate the vacuum solution, I work on the hypothesis that the order field that fluctuates around is in the ground state of the theory, and only this term and a constant is defined as the Higgs potential.
So
The term that exits only the Higgs field is the Higgs potential. And this term is an interaction, the A and the exponential term.
You mean in the vacuum you kind of consider other fields to be equal to zero?
Yes, it's classically, but I have never go to the quantum correction like the comment Bible. But I think it is just a new problem. Maybe รุ่นน้อง ครับ
Because it's a bit tricky to understand this new action. I mean, because you have like potential terms multiplied kind of everywhere. I'm not saying there is anything wrong or something. I'm not familiar.
I don't sure it because of the when you expand it, it's not only the Higgs field. There is not only the Higgs field, it's the Higgs and the other particle. It means that it's interaction term, not the Higgs potential. That's in my opinion. I don't sure that is my concept is true or not.
Yeah, and you would also have more types of interaction terms.
Because I think when you apply the Higgs in, for example, in the effective field theory, we have 3 Higgs coupling with the, for example, the 4 Higgs cell coupling with the fermion in the Lagrangian. This term is not calculated when you find the vacuum expectation of the Higgs field in the standard model effective Lagrangian as well. I think the term that you told me that the A term multiplied by the V, when you expand the exponential, it exists like the higher dimension operator interaction. And traditionally, I have never seen those terms is calculated to find the vacuum solution of the Higgs.
Okay, if there is no more questions, let us thank our speaker. Okay, please do not forget to fill in our questionnaires. Thanks everyone for joining. See you in the next seminar.
ครับ